Question 4. The acceleration little g due to gravity on a spherical planet in any universe is given by little g equals gm over r squared, where m is the mass, r is the radius of the planet, and g is the gravitational constant in that planet's universe. Apologies in advance, I know I'll probably say g when I mean little g. Please just bear with me, it should make sense when I write it all down. In a different universe, the gravitational constant is g dash and has twice the value of the gravitational constant in our universe, g. Find the ratio g planet over g Earth for a planet in a different universe which has half the radius, twice the density of Earth. So there's a lot to digest here, kind of similar to the last question. There was quite a lot to digest and a lot of good information given in the question. So the way I like to start these questions is just by writing down exactly what we know. It's clear and obvious because they've given you the equation at the top that we're going to need that equation. This one, g equals gm over r squared. Let's see what else we are given in the question. We care about the universe having twice our value of g. So what does that mean? That means that g dash equals 2g. Next, we are also told a planet has half the radius. So then we can say that r dashed equals r over 2, where it should be clear that the dashes represent the other universe. And let's be consistent with the question just to make our lives easier. And the other bit of information we have is the planet has twice the density of Earth. So let's say rho dash equals 2 rho. Okay, what else do we know? Well, equation 1, let's call it, has everything in terms of the mass and the radius. It doesn't have anything in terms of density. So just to make our lives easier, let's write equation 1 containing a density term instead of a mass term. Okay, so the way we do that is we take what we know is density, which is rho equals density equals mass over volume. So for the planet for Earth, let's call the density of Earth rho. The mass of Earth can be big M, and the volume is, well, the Earth, we can assume for this question, is a sphere. So 4/3 pi r cubed. Okay, so good so far. Now, if we combine equations 1 and 2, equation 2 being this density equation, what do we get? Well, we get g equals g, big G, times m, which we can get from equation 2, we know is 4/3 rho pi r cubed divided by r squared, which equals 4/3 big G rho pi r. Okay, so this is good. We now have G in terms of rho and r, which, as you can see here, I'll use a different color. These are the things we're given in the question. Okay, so I just need a bit more space. Switching my pen back. We have that. Well, we want the ratio now. Basically, let's jump straight into the ratio. G GP, I'm going to call it, over GE. So using our nice new equation here, which I'll call equation 3, GP equals 4/3 big G dash, because this is the planet in a different universe, rho dash pi r dash, divided by G of Earth, which is nice and simple, 4/3 G rho pi r. Okay, we can see that the pi's cancel, 4/3 cancels, and now let's use the information that the question has told us already, namely stuff that I've sort of underlined in yellow here. We know that G dash is actually 2G. We know that rho dash is 2 rho. We know that R dash is R over 2. So immediately we see that this cancels. The twos can cancel off. And then again, we've got a G, a rho, and an R. The rho's cancel, the R's cancel, the G's cancel, and in the end we're left with 2. So writing that out nicely, we've got GP over GE equals 2. Therefore, the answer, as we can see, is A.